So before we move on to discussing the technology, the process technology and the manufacturing of FinFET and Tri-Gate transistors, I wanted to give you a brief motivation of why there is a need for Tri-Gate or FinFET or fully depleted SOI kind of devices. What's the need for moving from a planar to this architecture? So this schematic over here, it shows you a conventional planar transistor where the source, the channel and the drain are in the same plane. And drawn here is the band diagram showing the conduction and the valence band of a long channel transistor device, assuming it's an N MOSFET device, so it's N source drain region and a P channel. So this would be the N source and the drain, and this would be the channel region. So this is showing the band diagram. So for electrons presence in the source region, they essentially see a barrier for going to the drain. And when you apply a gate field, you essentially, as you keep on applying a gate field, you move and you negate this barrier, and then electrons can now flow from your source and drain. So this is how it manifests itself in the ID/VG characteristics of the transistor. So plotted here is essentially the drain current in a log scale as a function of the gate voltage. So what you see is essentially as you apply a gate field or a gate voltage and lower this barrier for electrons to flow from the source to the drain, what you essentially see is an exponential increase in your drain current as your function of your gate voltage. So two things to point out here is essentially the slope of this exponential increase, which is also known as the subthreshold slope or denoted by SS. And another thing to point out is the voltage at which you start seeing this exponential increase. So that is also known as the threshold voltage or the VT. Note that this is a very simple definition of VT. There are more mathematical definitions of VT, but just for the sake of simplicity, let's just define VT at looking at this curve, the point at which we start to see this exponential increase in our drain current. So what happens in a conventional long channel transistor, when you go from say a drain voltage of a 10 millivolt to a drain voltage of 1 volt, so say you increase your drain voltage by 100x. So in a long channel transistor, what that translates into, you see a 100x increase in your drain current in your off state. You also see a same 100x improvement in your drain current in your on state. So what you essentially observe in a long channel device is that you observe the same increase in your current in the off and the on state, and your subthreshold slope also going from 10 millivolt to 1 volt, it does not change. So say the subthreshold slope here was 90 millivolt per decade. So you see the same subthreshold slope when you go from a lower drain voltage to a higher drain voltage. And your threshold voltage, your threshold voltage, say you had a threshold voltage of 0.1 at 10 millivolts. So you see the same threshold voltage at when you have a drain voltage of 1 volt. So three things are happening. Your subthreshold slope remains the same, your VT remains the same, and you see a similar increase in your on current and your off current in a long channel device. So another way to state that is from looking at this energy band diagram for a long channel device, whether you apply a drain voltage, a small drain voltage of 10 millivolt versus if you apply a large drain voltage, say of 1 volt, you're not modulating this barrier, which essentially determines your current flow from your source to your drain. So your drain voltage is not modulating this barrier for electron flow from the source to the drain. So now let's look at what happens when you have a short channel device. Say you have a device which has a gate length of 30 nanometers, which is typical of today's technology. So it's a short channel device, and plotted here is a band diagram, the conduction band and the valence band. So this is plotted at a low drain voltage of 10 millivolts, and this is at a high drain voltage of 1 volt. So what you see at low drain voltage, things look normal. As you apply a gate field, you see a decrease in this barrier, and again as your flow of your electrons from your source to your drain is still controlled by this barrier, which is in effect controlled by the gate field or the gate voltage, and you see a similar exponential increase in your drain current starting at the threshold voltage, and you see a similar subthreshold slope of let's say 90 millivolts per decade. But now look what happens if you apply a high drain voltage. So since your drain is now very close, it's only 30 nanometer away from your source, what you see is now applying a high voltage on your drain, this drain voltage tends to affect this potential barrier which exists for electrons to flow from the source to the drain. So what you see is the lowering of this barrier. So what you see is essentially the drain voltage, or the drain is inducing a lowering of this barrier. So which is also known as drain induced barrier lowering, or the acronym for this is DIBBLE. So what you essentially see is that now the barrier for the carriers to flow from the source to drain is being affected not by just the gate field, but it's also starting to getting affected by this application of this drain voltage. So how does it manifest, this thing manifest on the IV characteristic? So what you see is now when you apply a high drain voltage, say you apply a drain voltage of 1 volt, so there's a 100x increase in your drain voltage. So what you see is a similar 100x improvement in your drain current, but you see a much larger increase in your off state. So in your off current, you see a much larger increase. Why this is happening is because now, even though you are not applying any gate voltage, you are reducing this barrier for electrons to go from your source to the drain because of applying this high drain voltage. So this high drain voltage is essentially reducing this barrier, and so you're getting a much larger increase in your off current. Another way this can be demonstrated is you are essentially also in this graph seeing that your threshold voltage, which was now initially say 0.1 volt, now it has shifted, and let's say in this case it's minus 0.1 volt. So there's a 200 millivolt shift in your threshold voltage on the application of 1 volt of drain voltage. So your drain application of 1 volt of drain voltage has reduced your barrier, which it manifests itself as a shift in your VT. So one measure of this DIBBLE is your shift in your VT as you apply a drain voltage. Another thing you notice here is now your subthreshold swing is degraded. So initially you needed 90 millivolt to increase your on current by 1 decade. Now your subthreshold swing has correspondingly degraded, let's say 120 millivolt per decade. So there are three things which we can call as short channel effects. So what you see is in a short channel planar device, you see a shift in your threshold voltage, which is also, you can quantify it as dibble. You see your subthreshold slope degrade. So in this case, it's changing from 90 millivolts per decade to 120 millivolt per decade. And also you see a much larger increase in your off current. So you see an I off increase. So these three things are what is commonly quantified as the short channel effects. So what you see is increase in your threshold, decrease in your threshold voltage. So 200 millivolt for application of 1 volt of drain voltage. You see a degradation in your subthreshold slope, and you see a corresponding increase in your off current.